Coders, hello. Step 38 today is a big step, a sizable step. We're going to add multiplayer capabilities, and also the option is presented to the player to select either one of the possible players. So the original character in the game is called Dean. And Dean, as we all know, has a gun, and he collects bullets, and he has like a recoil moment where he can't shoot for a while, and when he stands still, he reloads his bullets. Now, Sam is a different character. He has a magic ability. Basically, the player has to fire, and then when he hits an enemy, as long as he keeps fire pressed, the enemy is held in position. And the longer he holds him, the more the enemy is hurt, and it eventually dies. Now, this game obviously wasn't designed with two players in mind. I mean, it's still early in the development, so it's a good time to add functionality like this. But you can kind of see in certain places that it's sort of shoehorned in, and it's not too bad. But it does indicate that, well, some design choices are better made at the start of a project than at the end. It doesn't lead to a lot of problems. I mean, the code is elegantly set up enough to allow for an addition like this. But by now we have data tables with 3 different types of indexes, meaning that when I find out the enemy type of a certain sprite, that is an index into one table. But if I want to use that index in another table, I have to either increase or decrease the index number by either 1 or 2, depending on which table I'm going to access. And that is kind of a pain. And if you're going through the code cold without knowing that, you're going to be wondering, why the hell are we decreasing this value, or why are we increasing it, or why by 1, why by 2? There's no clear explanation, but this is it. You know, it's a design choice. We didn't want to waste any bytes in the tables, so we came up with tables, and now they have all kinds of different ways of indexing. Let's have a look quickly at what it looks like. This video is going to be a little bit longer than the others because it's just a lot of ground to cover. I'm going to try to skip over the obvious changes as much as I can and just stick with the more substantial stuff. Did I not press? Yeah. Okay. The first thing to look out for is the selection screen. And I'll see there's now an option. Single player Dean. Single player Sam. Cooperative play. So I can have one player, I can have 2 players, or you know, and I can have either type of player. So that's a lot of checking. Also, and this is going to be important, when I press up, there's an immediate change. But when I keep pressing up, it doesn't scroll. It doesn't keep going. So it stops. It checks whether I've released the button, yes or no, right? And I can't go down. I can only go up. So we know Dean. Let's try Sam. I press... this is Sam. He looks a little bit different. And then there I go. I'm keeping it. See the enemy flash, and there he goes. So I hold him, and then I let him go again, and then I hold him again, and he's dead. I'm going to get this pickup. I don't know. We're not really playing the game. See, I can't see where that other enemy is not being hit now. Oh, so when I'm holding one enemy, I can't hold another enemy, so I can hold only one enemy at a time. There's bullets, and I can pick them up, but they, of course, they don't make any difference when I'm Sam. But Sam is a lot more powerful against these spiders than Dean was. So, but that's the way that it looks. I died immediately there. So I can put in my name. It's not important. So, as we're used to doing, we are going to look at the data first. There's a couple of toggles, up release, down release. These are just booleans, all right? It's 1 byte, yes or no. And we'll see how they are used in a minute. Then confusingly named variable here, player fire pressed time. It sounds like it's like a counter which keeps track of the amount of time that the fire is being pressed, but that is not true. This is also used as a toggle right now, but you can see 2 bytes, 1 for each player. So many of these tables that used to be for 1 player are now for 2. So we have to be checking what the current sprite number is in the code, and then use that as an index into these tables. Players' lives, for instance, is now 2 bytes instead of 1 for each player, and so on. Player standstill time, blah blah blah. Also, I have a player joystick port, which is not a port number, which is 0 and 1, so that I can add it to the actual joystick port address. Now, in the Commodore 64, DC00 is for joystick port 2, the default port, and DC01 is the joystick port 1. We expect, or we assume that the player expects the if I do a 1-player game, that we use joystick port 2. This is regardless of whether we choose Dean or Sam as our player. So if it's Dean, it always goes to the 0 port. If we choose Sam, we also want it to go to the 0 port. Only if we have Sam and Dean playing do we actually use joystick port 1. So that's a kind of behavior that we need to keep track of. There is a byte called sprite held. As you can see, there's only 1 byte. This will hold the sprite number of the sprite that is being held. So if it's 0, no sprite is being held. If there's a value in there, we can see that there is a sprite being held and which one it is. Keep in mind again that the functions that this behavior is being handled by is called on every frame. So we jump out of this function, and then in the next frame we jump back in, and that's the way that we check, is fire still being held? Is there still a sprite being held? And so we don't do any looping inside of the function itself. If you think I'm talking nonsense, you don't understand what I'm saying, we'll get to it when we go into the function. Yes. For some reason there is we have one of the things to animate and handle all the objects, we use a loop, as I just said, and one of the objects is the player control, right? So player control is not called by the game loop per se. It is called because there's an object of type player, and its behavior routine is called. It's called for Dean here, but it's also called for Sam here. Now, this the player control function is huge and complicated. I would have selected to make 2 different player control functions, one for Dean and one for Sam. We have that for every different kind of enemy, so why not for the player? No, we have 1 player control function, and it is a monster by now. If you just ran into that function, even with all the code and all the semantics in it, it's hard to understand. If you used a machine code monitor and tried to analyze what that function did without all the semantics, good luck, dude. It's hard. Here you can see that we're sort of running into a little bit of trouble because according to this table, our new player Sam is actually an enemy and it needs an entry in this table because we can't skip because of that indexing problem, right? So now we have a dummy entry. Okay. You could ask yourself, why is there an entry here? Yeah, okay. It's at least it's a dummy entry because this never gets called, right? Because when Sam gets hurt, nothing really happens. We could, but now it's just dummy information. Of course, there is a player Dean, and there's a player Sam for the enemy types. Again, this table is indexed. There's a dummy entry here, so that's one of the reasons why we have to be careful with our indexing. Player Sam also needs an initial sprite standing in the right direction, just like Dean does. Sam has a start color. Sam has a toggle for multicolor, yes or no. Explosion, again, the first ones here are all dummy entries. Then health points for player Sam. I guess we just have one hit and we're dead. Yeah, we could experiment with that. What's our annoyed color for Dean and Sam? They're both color 10. What is color 10? Can I see that here quickly? Oh, color 10 is like the red thing. Oh, and you can immediately look at what Sam looks like. This is Dean. Dean has a really big jaw for some reason, and Sam does not. Sam looks more like a regular dude. And he has a different kind of walking style. I'm not exactly sure what this is. Is this multicolor? Okay, there we go. Oh, this is his... there's a couple of empty ones here. Maybe we just... I'm getting ahead of myself. I realize that. But there's something different here. There's 2 sprites here that are empty, so maybe that's for later. And I there's also... What is this? Oh, I picked a weird color here. Okay. Anyway, getting ahead of myself. New sprites. I think that's probably the next subject. Is type enemy. All of these, or some of these tables, again, that were meant for one player, just now have an extra byte. So we've sort of doubled the amount of data we use because we have an extra player. Of course, there are different kinds of texts which we have to check for. Text press fire is the same. But if we're playing with Dean only, we have a Dean score. We play with Sam only. We have a Sam text which sits at a different place, and Dean and Sam together, they look like this. Remember that we update these numbers directly on the screen, so Also, good to note, and we'll see that again, I think, in the code. We have a fixed amount here. This just prints 3. If I decided as a programmer that either Dean or Sam will start with more lives, I have to remember that I change this text as well, because that's going to be confusing. There's a text for the game mode that we saw. This is just a table of addresses. 3 game modes there are: single player Dean, single player Sam, co-op play. Get ready, nothing's changed there. Let's see, drive number, it's not changed. Oh yeah, of course we have the game mode somewhere. There is the game mode default. It's just this value, single player Dean. Then in the level development and the level definitions, of course we have to locate the new objects, because even if we and we have to make sure that when we draw a level, we do or do not draw these or place these objects in accordance with the game mode that the player chose. But we have to mention the objects, otherwise there's going to be levels where either Dean or Sam just aren't going to show. So we could make it's again. It's also an interesting kind of gameplay, because you could make Dean only levels or Sam only levels. If you're in a co-op play, then all of a sudden Sam has a level, or Dean. That's it for the data. So I'm going to scroll way back up, and I'm going to jump to the first change here. What? Yep, and we're going to go through the code changes. There's a couple of constants. Again, only the important stuff I'll mention. And of course, well, we have new sprites, but we had already seen that. See that? This is the whole Sam block. So we saw, for some reason, this is the sprite base. I seem to remember that it was 49. Didn't I just see that? That 49 was noted as the initial sprite for Sam. Object type constants, yeah, we have some new constants that are going to help us. A player type for Dean and a player type for Sam, of course. It's called player type Dean now and not just player type. And then we have the game types, 0, 1, or 2. Also, no big deal. Okay. Then next we have to show the current game mode when we're starting up. That happens here. There we go. So we just load the, we just get the game mode into X. And then load the address for the appropriate text, and then just call. What do we do here? I think parameter 1 and 2. I think are location, and then display text. Just prints the text. So that's easy enough. So this puts the game mode actually on the title screen. Now, this is where the fun starts. Now we have to read the joystick. And I kind of wrote the function in C, or a sort of a pseudo language, in order to make sense of it. So this is the logic. If we're not, we read the joystick, yeah? If we're not pressing up, then we don't do anything. Well, we do something because we set up released, which is a toggle, to true, because we're not doing anything and pressing up is released. Now, as soon as we do press up, we check whether up is released. And the first time we get through here, it says, yes, up is released. So we get in here, we change the game mode, and we set up released to false. Well, technically, we're still holding it, right? So it falls through, and then if we're still pressing up on the next loop through this function, yes, we're pressing up. Up released by this time is false. So we basically do nothing. And that keeps happening until we release up again, because then we go through this check and up is no longer pressed, and we set up release to true. You kind of see this kind of a two-step process to get this behavior going. So what does that... This is like the pseudocode. Now let's look at what this looks like in assembly. Okay, we load the accumulator with 1, and we do a bit operation on the contents of the joystick port, which basically means that we do an AND. You have to realize that when you do nothing, all the bits in the joystick port are set. And if you press up, for instance, the first bit will be pulled down to 0. Yeah, so it's sort of inverted behavior. The result of that AND operation will influence the 0 flag, and that is what the branch here tests for. So it's kind of something to get your head around. Anyway, if you don't do anything, you get basically a 1 and a 1. The result will be 1, and the 0 flag will be cleared. So if you do nothing, then up is not pressed. When up is not pressed, so we're basically doing nothing, the first thing we do at the end of the loop is to set the accumulator to 1 and store that value in up released. So we're setting up released. And then we drop out. The next frame, we do the same test again, but what if we pressed up now, then we go through here, and all of a sudden we load up released, and we notice that it is now set. So if branch equals 0, then then we go to the up pressed branch, which basically does nothing, which is this line. But we go on now, and then we increase the game mode. We load the game mode, make sure that it is when it is 3, that we make sure to wrap it back to 0. Otherwise, we don't do a game wrap, and we display a new a game mode. Right? We do that just the same as we did before. Then we load 0 into the accumulator and jump to up pressed, which stores that in up released. So you get the same behavior here in assembly as you do in this pseudocode. It's just that you have to do it with weird jumps to the end, right? So jump here or jump there. That's how you get the that's how you get the same thing. So this is a bit confusing, perhaps, because of the way the joystick port works and the logic. But you want this behavior. You don't want to keep scrolling. If you wanted to keep the thing scrolling, you'd have to change this kind of routine. But the scrolling would be very quick, so you'd have to then introduce some sort of delay so that the scrolling doesn't go too fast. Otherwise, it wouldn't be usable. Okay, enough of that. Next. Okay, I'm going to show you this short. Where do we the player lives? Okay, there we go. This is the initialization of the game. We have to set the player lives of both the players. So we set number 3 in player lives and player lives plus 1. So remember just now that I said that on screen in the text it says 3, and this is where the data initialization happens. If I wanted to make this 5, for a brief moment perhaps, it would say 3 on the screen because that's what was printed. Let's try that. If I made this 5, see what happens. Do I immediately see 5? Because that would make us lucky, because then it's probably overwritten somewhere. Okay, let's play. See, I made that 5. I'm pretty sure I made that 5. If I die now, it'll probably be 4. Die 4. See that? So that's how you introduce bugs. Yeah. I mean, it's good thinking probably to say, oh, I'm going to print 3 there, but that makes you forget to actually print this value on the screen. So you get a weird bug, and then you'll have a tester maybe one day, and they'll find it. But as a programmer, it's easy to overlook this. Anyway, the display, yeah. So what we do? We load the game mode. If it's single player Dean, then we jump to Dean only. Then we compare it to single player Sam. Then we jump to Sam only, and in any other case we do the Dean and Sam text. That is the bottom section of the screen. Dean only, we set A to 0. We store that in player lives plus 1. Really? Dean only. Dean only. That's funny because I thought Dean would be player lives 0, but this looks like a bug to me as well. This would have to be Sam only, and this would have to be Dean only in my book, but because they're both the same, it doesn't really matter. But this is not, logically, it doesn't make any sense. Dean would be, it would have to be like this. I think this would make more sense to me. Anyway, display. What a nice comment. Settings per game mode. Let's see. Oh, right. Yeah. Okay, so set player 0 to port 0 and player 1 to 1, right? So player joystick port and player joystick port plus 1. That is how the data was initialized as well. So this doesn't really change much. Now we load the game mode, and if it's just single player Sam, if that's not the case, then forget it. If it is the case, then we set 0 to player joystick port plus 1. So Sam's joystick port will become 0, meaning effectively it'll be added to DC00, which means port 2. So this is the stuff that you run into if you're programming for the Commodore 64. This has got nothing to do with assembly. This has just got to do with knowing that the Commodore 64 has a quirk with these port numbers, and that's just one of the simple quirks. There's lots of them, but that's what makes it fun. That's how you know the Commodore 64. Yeah. This is the game loop, right? So this is where the game is actually started. So we could technically, I suppose, check for collisions for a player that isn't there. If we chose to play single player Sam or single player Dean, we don't have to check collisions for the other player if he's not literally on screen. because we don't use hardware collision detection, we do it by software. So quite possibly the information about where he is still there. He may just be drawn, or well, not drawn. He may just be set to be drawn in the starting position, and we might get a collision detection. So we actually choose to skip it here. So we in each loop of the game we load the game mode. We compare it to, is it game type single player SAM? If it's equal to that, then we no collision check for Dean. So check collisions now has a parameter X that will let us check for a specific player. So we'll go to start level. Find it. There we go. The start of a level, we have to now initialize some values. So player stand still time. Again, this doesn't really hold a time, but just it counts up on every frame. Player invincible. These are now all 2-byte tables, so one for Dean, one for Sam. Again, invincible, one for Dean, one for Sam. You're invincible right after you have a like a power up. This game does not let you be invincible after you die. After you've died, you get the little animation. You come back, you're vulnerable straight away. But you can have a pickup that makes you invincible for a certain amount of time. Player pressed fire time +1. As you can see, again, this is just a count, but we only set this for Sam. Dean does not have a functionality that will change when he keeps fire pressed. Doesn't. In fact, when you keep fire pressed, you fire one bullet and then you have like a recoil time and you have to wait. This is where the X parameter comes in. It didn't used to have the X parameter, so now we check. Well, we did check whether the player sprite was active. Now we check for the correct sprite number, 0 or 1, Dean or Sam. We start with index 0. So we start by checking collisions for every object. So this is used to check whether the player collides with an enemy. And then we loop through all of the objects. And then in this version of the code, we specifically add this. So start with sprite 0 to check for collisions. Now, I made a note here that this makes no sense to me because sprite 0 is never an enemy. It's always a player, so it makes no sense to start at 0. Sprite 1 might be an enemy it might be an enemy if we're not in co-op mode, or if we're in co-op mode and one of the players is dead. So it makes sense to start at sprite number 1, but starting at sprite 0 is just extra time. So I can't really explain that one, but it has little effect. It just does a little extra check. The thing is, it'll always end up here. Is it an enemy? And the first, if X is 0, we'll always run into this, and it'll always be false for that sprite. It'll always be no. So, and then we jump out. But that's just a bit of code that doesn't have to be executed, in my view. Maybe I'm wrong. So still in this check collisions function at the end, there's something that we need to make sure of doing. If we're player Sam, at the end of the of this function, we are in the section where we checked everything and the player has actually collided with an enemy, and that kills the player. Now, if we're playing Sam and if we're checking for Sam, so if we compare with type player Sam, if player was Dean, then we can jump out. But if we were Sam, then we have to make sure that the sprite held value is set to 0. So that means that if we're holding an enemy and a different enemy kills us, that the enemy we were holding is then released. So on the next loop, we'll see that no sprite is held, and the sprite will just keep animating. Okay, so in this function, is enemy colliding with player? We've talked about this in a previous video, so I'm not going through the whole thing. One of the things is that this used to be simple when we had just one player, because the calculate simple x position function simply took x as the player number, which was 0 in this case always. So previously in the code, this said load x with 0 and then call this function. But now y holds the actual player number. But we have to transfer y into x now, or change the parameter to y, but that will not work because we want to have it in x, because we want to use it as an index. But the 6510 or the 6502 chip doesn't have a function that will allow you to transfer a value from y to x or x to y. So you have to go through the accumulator. Also, you have to. So then now you have to store. We already did that. We stored the accumulator in parameter 1 anyway. So we transfer y to a, we transfer a to x, and then we call this. So we have some extra transfers to do here. And I'm looking at this as why does this happen? Why do we need this? But that's just because this uses x. And now the player number is actually matters. Yeah. So the next function that we're going to talk about is player control. I think in the previous video I already mentioned that player control has already become so large that we've had to make changes because the branches were becoming too big. We can't branch more than 128 bytes forward and not more than 127 bytes backward. The entry point to player control isn't at the start of player control. It's somewhere halfway down the middle. The game is over if both players are dead. Yeah. So if the sum of the lives of both players is 0, then does the game end and not before. So what we do is we load the number of lives for player Dean. We're going to add, so we need to clear the carry, otherwise we're adding an extra 1. We add with carry the number of players of player Sam. If it's not 0, then other players are still alive, and we remove the dead the dead player. And only in the case that it is, if the sum is 0, do we go check for high score. Check for high score call is end of game in this code. This is for refilling the shells. As you saw, I can pick up, as player Sam, I can pick up a bullet pickup, but I don't want this code to start drawing bullets on the screen while I'm not using them. So this is where I have to check for Sam or Dean. So there are plenty of places in the code where you have to make this simple check. Are we Sam or are we Dean? And do we do one thing or do we do the other thing? This is also because all of the player control has all been condensed into one function. It makes it kind of hard to read. This is funny. Oh yeah, this is funny. When we initialize the enemy values, we load the sprite player shape, yeah, this should be indexed. It isn't. It should be. And the sprite pointer base for either Dean or Sam is always initialized to the shape of player Dean. So you don't see that because on the next frame we're probably already updated to the right value, as we saw, because we changed that. But technically we're being initialized to the wrong shape if we're player Sam. Again, it's one of those little tiny bugs that you never find, and you can have bugs in the code that don't lead to any faults on the screen, which is good. The other things, when we're resetting the player, is fast reload. This is one of those pickups, where you have a fast reload. That's only for Sam. Player invincible, that's for Sam and Dean both. Sprite state, are we vulnerable, yes or no? And player fire press time, we set that to 0. Jumping and falling positions, all the same. But this is where the entry into player control is. This is where we check whether the player. Remember, we're in player control, and we've done the dead checking, and we've done the item pickup checking. Now we're going to see whether the player is moved. So we load the value of the player joystick port, which is 0 or 1, indexed by the player number 0 or 1. So the first position in this, or the second position, will give us 0 or 1, and that is added. Y is added to joystick port 2. So DC00 port 2 and DC01 is port 1. This is where it happens, because now when the player's pressed fire, if it's Dean, then it's Dean, right? This was the Dean code. But now we have to see what happens when Sam fires. So if X is 1, then we're Sam, and we have to handle his type of firing. So let's now look at that. So we have to do all this holding and all that. So anyway, we get the correct joystick port, which can be either 0 or 1, depending on single player Sam or co-op. If we didn't press fire, then nothing happens. Easy enough. But we're interested in what happens when we did press fire. Now, pressed fire time is just set to 1. So this means that we're using it just as a toggle, because every time we go in here, it just goes to 1. It doesn't really matter how long we pressed, as long as we are still pressing it. So the player pressed fire time, it's set, yes, we're pressing fire. We store X to parameter 6, and then we do the Sam use force. This is where the magic happens, and it comes back with a value in the accumulator saying whether or not an enemy is being held. Right? We'll have a look at the code in a minute. If it's 0, then no enemy was held, and that's basically jumping to fire done, and we're ready. If an enemy was held, then we increase the player shot pause, because we want to measure that he doesn't press it any long. He only needs to press it for 40 frames. Right, so by increasing this value, we make sure that on the next pass of this game loop, it'll be 1 more, right? So, and then we load the value, we compare it to 40, decimal 40 here. If it's 0, so if we've reached 40, then the enemy was hurt by Sam. If not, we and this is one of those cases that I talked of before. We get the sprite type of the sprite that is being held, and we have to set it to red. But the VIC sprite color table has a different index to this one, so we decrease the index. And then we load red, and we store that in the Vic sprite color for the correct sprite. Otherwise, the wrong sprite might become red. So as long as we're holding fire, and the sprite that is held is turned red. Yeah. Now, after 40 frames, the enemy is hurt by Sam. Enemy was hurt by Sam. There we go. We set the player shot pause to 0. We load the sprite type of the sprite that is being held. We decrease it. We set it to 0, which is black. So it only turns red when it's in that 40 frame loop. But now we're out of that. So we return it to 0. We decrease the sprite's health points. If it's not equal, then the enemy was hurt, and basically we jump out. If it is 0, then we add 5 to the score. We get the sprite type number, adjust the index, and kill the enemy. Yeah? And then afterwards, we set the sprite held to 0, and we jump to not fire pushed, which means we jump out. So we have to make sure that we're not already holding a sprite when this happens. So we load sprite. If it is equal to 0, then no sprite is being held. Now, if there's already a sprite in there, then we just can return with 1 in the accumulator, saying that yes, we're holding a sprite. If we weren't holding a sprite already, then we get the sprite number of the player. We get our Y position. Our Y position is determined by our feet. Yes, so, and when you shoot, you have to also take into account that the sprite is like 2 characters high. So the sprites that are on the level of your head also have to be hit. So that's why this remark is wrong. We don't adjust any index. We just look at the line above. So we get the Y position in Y. We get the start of that line. Then we get the X position in Y. So long story short, Y now contains the X position of our shot, and parameter 6 contains the sprite index of the player. Now we have to determine the direction. If we're shooting right, then we go to shoot right. Otherwise, we're shooting left, and our shot goes 1 character to the left. We have to see whatever is there and check that whatever is there is not blocking, because we can't shoot through walls, right? If there is a blocking character in the way, then this ends our shot. If it's blocking, then we just end. Otherwise, we have to check hit enemy, which is this one, and then we have to loop through all of the active sprites to see if whatever we encounter is actually an enemy. We have to check whether it is vulnerable. So we load the sprite state, and we check whether it is above 128. If it is, then we have to see whether or not, and this is collision detection in software, right? So we check the X position, then we load the Y position into A. We compare that to that of the shot. If it's equal, then the enemy is hit. If it's not equal, we also check whether or not it is hit on the line below us, or if it is hit on the line above us. If that all checks out, then the enemy is hit. So If finally the enemy is hit, we store its value in the sprite held field, and we increase that, and this is one of those index repair actions. And then we have to call for this sprite its hit behavior function, because that is not hit, that is not called by the game loop. So what we do is we get the sprite active type. We have to now decrease that index to get the address of the hit behavior function. What we also do is we take the address of the shot done hit. I don't know, where is that? Where is that? Shot done hit is this RTS with this address. Shot done hit -1. We push it onto the stack, which is the high end, and then we do the same for the low end. We subtract 1 because that's what an RTS does. It expects an address that is 1 lower because it adds it once it pops the address. We jump to whatever address that is, and at the end of that function, there's an RTS, and that RTS will pop the address off the stack, which is what we've put here, and then it'll just jump back here to the RTS. Sip of water for that function, eh? Jesus Christ. The most important thing in this function in the end is this, that we're able to store the sprite held thing. Once that's done, once we know the sprite number of the sprite that we're holding, that's it. And then we have to return with 1. We have to, because this is going to be the return function, and we have to make sure that this hit behavior function doesn't overwrite the value that we set here, because that could lead to all kinds of weird bugs as well, because the function expects 1 to be returned if we're holding a sprite. Object control. Look here, all of the code, now that we've set sprite held, object control is in charge of moving objects. So if we're trying to move an object that is currently being held, and we store it in parameter 1, we decrease parameter 1, we compare it to X, same thing, index stuff, then we just skip it. So this makes sure that whatever sprite is being held, it doesn't move. Okay. Let's look at how these levels are drawn. In each level, there is a player Sam and a player Dean object, but we have to decide whether or not we are drawing them actually. So if we run into an object, it can be any object, but if we run into a player Sam object, if it's no problem, if it's not player Sam, then we just continue. If it is Sam, we have to make sure, what's the game mode. If it's in single player Dean mode, then we shouldn't spawn the object and just continue. Otherwise, it could be co-op mode, but we have to put player Sam in location 1 and not in 0. Now, if we weren't drawing player Sam, we have to, of course, do a similar check for player Dean. If we're drawing Dean, if it's not Dean, then it's something else, and we just continue. Otherwise, we have to check the mode, and if we're in single-player Sam mode, then we obviously don't spawn the object, and otherwise we do. We do have a challenge here, because finding an empty sprite slot would normally just find the first empty sprite slot, but we want to, in the case of Sam, we want to find an empty sprite slot starting with, not 0, starting with 1. So this is very simply done. If we go to the declaration of this, then you'll see that find an empty sprite slot will normally just start with 0, But if we load a value in X and then jump to this, it'll just not set it to 0 and do the same check and find the first empty thing. And with that, I've finally done everything that is in this code. It's been a long one and it's been a complex one. I'm hoping that I made sense. But anyway, thanks for watching.